hopefully from the lunch you got some appreciation of how, number one, it's doable to transform a regular matrix vector multiply into this, but it's non-trivial. Number two, if you were to go and annotate either of these algorithms for correctness, you would have nested quantifiers. This would get pretty nasty. And if you actually wanted to turn it around and derive the algorithms to be correct, you would be in for quite a task. So what do we need to do? Well, we need to go and create notation. The first step is always notation. So let's go back to what we were doing here. Now notice that at some time in our process, we inherently have gotten to some point in the matrix. And in the regular matrix vector multiply, we would then expose a column or expose a row. But really what you want to do here is expose a row and expose a column because of symmetry. Okay? And notice that then you do some computation, and then really this orange line moves forward to here and the process continues. And this all is in an effort to cleanly identify a block of the matrix that is not stored, and then the corresponding block of the matrix and where it is stored. So what we want to do and capture with our notation is that picture. And if we can capture that picture, then maybe we can create some notation with which we can reason cleanly. Maybe we can come up with a partitioned matrix expression for this operation. Maybe we can then identify loop invariance. And with a little bit of luck, the magic algorithm that we're after that marches through the matrix by columns will just drop right in our lap. Wouldn't that be nice? Okay, well, let's see if we can get there. I'm going to go and erase all of this here. Okay, now we have a partially clean chalkboard. How do we start? We want to compute y is equal to a times x plus y. Okay? And that means that the post-condition for what we want to compute is y is equal to ax plus y hat. Okay? Now, A is symmetric. And we're just going to keep that in mind. Obviously, we might actually want to make that part of our precondition and carry that through, etc., etc. But you want to balance how much clutter you create with being extremely precise, with the benefits of keeping things relatively simple, and then just kind of keeping some facts in the back of your head as you're doing the derivation. So we're going to be, we're going to keep in mind that A is symmetric. All right. On the left here, the picture there motivated us to say maybe matrix A should be partitioned into quadrants. So let's take our matrix A and let's partition it into quadrants. Okay? What do we know? Because every time through we pick up a row and a column, when we keep moving through this matrix, we keep the quadrant, the top left quadrant, square, and therefore, because we started with a square matrix, the bottom right quadrant is going to be square as well always. So we know that this is square and this is square. What else do we know? We know that A is symmetric, and therefore we know that A top left is symmetric, and we know that A bottom right is symmetric. That's a property of symmetric matrices. Okay, just think about it. This whole matrix is a symmetric matrix, and this is a symmetric matrix. Well, it's 1 by 1, so it's a little bit hard to see, but you notice that this here is a symmetric matrix as well. The other thing you notice is that whatever matrix is sitting here is reflected up here. What was a column here becomes a row here. If it was more than that, then it would become the matrix there, but transposed. So, A is partitioned like that, but when you then take it and you plug it into the post condition, which is how we went about trying to find a partitioned matrix expression, what we can plug in is A top left, A bottom left, A bottom right, and up here we get A bottom left transpose because of symmetry. This is stored, this is not stored, but we do want to compute with it. Okay. Now, notice that in order to be able to now multiply times x, we're going to have to partition x into a top part and a bottom part, because the way partitioned matrix vector multiplication goes is you need to be able to do this times the first part of a vector plus this times the second part of the vector for the result. So, let me give myself a little bit of room. We're going to put in a partitioned vector x. Okay. And notice that what we find is that we end up doing this times that plus this times that, which creates a top part of a result vector, and this times that plus this times that, that creates a bottom part of a vector. And that tells us that y and y hat must be partitioned into a top part and a bottom part as well. Okay, so what did we just do? We took the post condition, we partitioned the operands, we then took the partitioned operands and we plugged it into the post condition. This tells us in terms of the partitioned operands what the final result needs to be. And now what we do is we do what we have done before, which is we apply the rules of linear algebra to this to manipulate this into something from which we then hopefully will be able to recognize a partitioned matrix expression. So how does that work? Well, partitioned matrix vector multiply goes just like multiplying with numbers. If these were numbers, you would do this times that plus this times that. So the top part here is A top left times X top plus A bottom left transpose times X bottom. Notice that these are mathematical expressions. This doesn't mean that you need to go and take that data and transpose it. It means you want to compute as if that part of the matrix was transposed. And then you have to add the corresponding part of y to it. You got it? Same thing for the bottom part. And our final result must be equal to that. Okay, now notice that this tells us exactly what the top part of y should be when we're done in terms of these different pieces, and what the bottom part of y should be done in terms of the different pieces. And that is our partitioned matrix expression. This is, if you think about it, a recursive definition of the operation. How is it recursive? This right here is a symmetric matrix vector multiply. This right here is a symmetric matrix vector multiply. Okay? So, we have the partitioned matrix expression. We hope we can take the partitioned matrix expression now, and from it, systematically come up with different loop invariants. And then, hopefully, among those loop invariants is one that magically will give us the algorithm that we want. Okay? How do you go from a partitioned matrix expression to a loop invariant? You say, well, we haven't done all of the work yet. So some of these terms that show up perhaps haven't been done yet. Okay? Because if this part of the computation hasn't been done yet, then at this point you aren't done yet. You're still iterating. You're staying in the loop. So what I want you to do is take a second and think about coming up with 2 loop invariants. And once you find 2 loop invariants, we'll discuss how you may be able to come up with many loop invariants. And the 2 loop invariants that I would like for you to try to find are the loop invariants that correspond to the algorithm that would go by rows if it was a matrix vector multiply where there was no symmetry, and the algorithm that similarly goes by columns. So the one by rows from top to bottom, the one by columns from left to right. Okay? Just take a minute and try to do that.